All right, so with logistics growth, it's similar but more involved than your exponential growth. So remember when we did our exponential growth, we said dy dt, the rate of change, is directly proportional to the amount present. As y grows, the rate grows faster. As the rate grows faster, y grows faster. So that gives us an exponential growth, and we have a way of remembering that model as CE to the KT, and we call that sometimes sect, all right? So you're going to have a different one. You're going to have to decide, is this a sect model, or is this it's actually Lice minus licked model, all right? So remember that we did some separation of variables to derive all that. We needed some points along the way to determine those two unknowns, but this growth continues not only forever, but faster and faster and forever and ever. And in the real world, things often start off that way, but there's usually something that causes it not to increase rapidly forever. There's usually what we call a limiting factor, which is why sometimes we use L in here. Maybe there's not enough space for any more growth. So suppose Peyton gets lice, right? It's going to grow exponentially on her head for a while, right? And more and more and more until at some point there's just no more space. And what will the lice do? Hop on you, okay? So, but at some point there is only so much space. Does that make sense? Rabbits grow exponentially for a while, but if they're in an enclosed space, at some point they're going to start to die off because there's too many, right? So in biology, sometimes it's like the food supply limits growth or the waste disposal mechanisms limit growth. So generally, what happens is a lot of times growth starts off exponentially, but then it tapers. All right, it still continues to grow. All right, but it reaches a maximum growth rate at. And we're going to go put that on here because that's going to be important. So this is usually what happens is the growth starts off exponentially, but then at some point it starts to increase, but it increases less rapidly. What is this called in calculus where we have that change in concavity? An inflection point. So that's going to be really important in our work, that we understand that the maximum growth occurs at the inflection point. This happens a lot with things that grow. Like I said with the lice, or like a rumor. I always say, hey, guess what? Sean was pregnant. It's a bad example. Hey, guess what? That rumor's going to spread rapidly at first. And you guys are going to take out your phones and just start texting people. It's going to go crazy throughout the school, right? And let's suppose it's confined to this school, right? At some point, you're going to go tell somebody in the hallway, and what are they going to say? I already know that, right? So there's a turning point in the growth. And it's mathematically derived because you guys just said it's at an inflection point, correct? And how do we find those from AB? Second derivative equal to 0. So when I derive where that occurs, that maximum growth rate, I'm going to use the calculus of it. All right? All right. So we call this limit up here. This is a limit. From pre-calculus, it was a horizontal asymptote, right? But in here, time is what's increasing forever, and it's the amount present at that time that's limited up there. We are going to call it the carrying capacity of the population. It's the maximum that the ecosystem can support. All right, so it depends on, if you guys were to go Google logistics growth, you would see that being called one of these 4 things. C for carrying capacity, L for limit, right? M for max, it's the most it'll ever be, and A, I think, for amount. I'm choosing L, but don't be tied to variables. I like the L so that you get that limit idea down. So up here, there's an L that stands for the carrying capacity. Let's do this. The limit as t approaches infinity of whatever's growing, which I'm calling Y, but it might be B for bacteria, right? Or it might be R for rabbits, or C for COVID. This was perfect last year at this time because we had just gone to distance learning, and in the news, this is why. It was reaching that inflection point, right? And then it started to taper off, but then it went off the logistics curve. Then it just started to kind of go wonky. But at the time we started this last year, it was following this, which was, so we had some really cool application. But then it just kind of, it would spike and then go down. It didn't follow that logistics model anymore. All right, so here we go. This is equal to L. Write that down, because a lot of times it won't say find it, actually it never will, because it's calculus class. It won't say what is the carrying capacity. It'll say what is the limit as t approaches infinity of R of t, or maybe R is radioactive material. It's not asking for carrying capacity. So understand that I should stay closer to the board here for the recording. So understand that up there. So we're going to start off with the DiffEq for it. This is how you get the rate of change. If I didn't have this, don't cross it off on your notes. What kind of growth is that? Go ahead and tell me. You can talk even though I'm recording. That's exponential growth. And it'd be y equals c e to the kt, where it's directly proportional to the amount there, and it just continues to grow faster and faster. But when I put this on here, this is the difference between the carrying capacity and the amount present. And as one goes up, the other goes down. So if the carrying capacity on her head is L for how much it can hold, as L goes up, this number is going to get smaller. It's the space left on her head. Does that make sense? It's the amount left there. It's the difference between the carrying capacity and what's already grown. So there's this way to remember it. Instead of the sect model, we a couple of years ago called it Kylie. And then they, oh, this is Kylie. K-Y, like a girl's name, right? The only problem with that is if you change it so that maybe it's bacteria growing over time, you have to understand it would be KB, right, times what? L. You have to transfer to different variables. So if you're going to kind of memorize little mnemonics, you have to not be variable dependent with them. Are you okay with that? So let's suppose it was, I want you to set it up. Suppose I tell you that moose in some national park were growing at a logistical rate. Okay, I want you, with a carrying capacity of L, I want you to put that into this model using an M. All right, so go ahead and write the rate of change. Use an M for moose so we're not Y dependent. You can still use an L for carrying capacity. Just so you understand the model. You can think Kylie, but you can't be variable dependent. All right, so you should have done the rate that the moose changing over time is directly proportional to the amount of moose present, right? And the space left in the ecosystem. Do you see how the math goes with the common sense of it? Are we good? All right, now if I said that that particular reserve or national park could only sustain 200 moose, then you need to know to replace the L with a 200. All right, so knowing, you guys are nodding, understanding the model is really important. K is what it's always been. It's a constant of proportionality. Okay, so it's some proportionality constant that might need to be found. All right, now I want to figure out, well, how do I get from the rate that COVID is spreading to how many people have it? So suppose it's spreading, correct, at a particular rate that's following this logistical growth model, right? And I want to figure out, well, 5 months from now, correct, how many people are going to have it? Maybe the hospitals can only support. Do you see that? That's super applicable, correct? Right? If we get to this spot pretty quickly and we can't support that continued growth, we've got a problem. All right, you ready? That's what, do you remember how we used to keep saying last year, the year before, flatten the curve? Right? You remember that phrase? That's get rid of that inflection point. Don't get there. Flatten it off first. All right, so let's go up here. We need to solve it for y. And this is where I could just have you Google it and give it to you, but there's, like I said, even though they have computer programs that do this now, somebody had to historically figure it out. How do I figure out how much is present at any given time? So guess what? Calc 1, it's going to turn into Calc 2 for a second, but what Calc 1 technique is going to help me solve for y? Yep, exactly. Just because I'm on video, he said separation of variables. So let's go do it. We keep all things y on the left. So we do 1 over y And if you don't understand the proof, that's okay. But there's really, you'll still be able to use what we get from it, but I really like it if some of you can understand. All right. Remember in this scenario, K is a constant, it's a number. L is a number. What does L stand for again? Remember? Carrying capacity of the ecosystem, yeah, or whatever space, like this room, and we just shut the door, you know? All right, and nothing else could leave or come in, right? At some point, we're gonna be killing each other out. All right, anyway, what do I do next? What do I do next up here? Yep, let's do it. All right. Now, this is why we really couldn't technically do this in Calc 1. Now, I want you to go over here. I know you know this guy is KT plus C. It's on the left, and don't blurt it. I'm going to take out the obscure new variables and put in old ones. You're used to integrating with an x and maybe a number and then a dx. Pause and don't blurt. We do have a new technique for integrating that. Gotta think about it. Is it integration by parts? Is it, I don't want to say it. Do you see it? What is it? What's that called? It's kind of a big word, but you know what it is. Do you remember? Yep, there it is. Thanks. Just so Hannah can hear, we said partial fraction decomposition. Exactly. That's why we couldn't do this last year. You didn't know how to do that. So we're going to go over here and kind of model what we do with our partial fraction decomposition. Are you all right with that? So I'm going to go back and let's go. We break this up. We'd say that the 1 over y times L minus y is equal to some constant over y plus some constant over L minus y. Good so far? This is good to review this anyway. Remember, we multiply the whole thing through by that denominator. It'll wipe it off on the left. Basically, it gives you crisscross over on the other side. So we have A times L minus y. Remember, L's a number, plus B times y. All right. Next up, do you remember what we do? You're used to x's and numbers. This is a formulaic approach. So what were you going to say, Caden? Yeah, we strategically choose y, correct? So that each of these pieces, we're used to strategically choosing x, but again, we can't be variable dependent. So I'm going to let y equal, let's say, L. You're nodding, right? It's kind of cool. All right, so y is going to equal L. It's going to wipe this off, right? So I would get BL is equal to 1. What's B? Or 1 over the carrying capacity, right? So if the ecosystem can support 1 million butterflies, it'd be 1 over 1 million. All right, so that's a 1 over L over the, and B was over my L minus y, right? Let's go find our A. So I want that, I'm going to put that one first. So for my A, what else could I strategically choose y to be? A 0. Right? Awesome. So if it was a 0, I would have 1 equals A times L minus 0, or AL. What's A also? 1 over L. Okay, so now I'm going to go back over here. I have 1 over L over Y, my A, plus 1 over L minus Y. Again, if you don't follow the proof, it's okay. You should at this point be able to handle it. How are we doing so far? We good? You're good. Awesome. So this is a constant right here. Whatever the carrying capacity is, it's 1 over it. And when we integrate, what do we always do with our constants? Move them to the front. So I'm going to do that as well. This is a number. The constant in this situation is the y. I mean the variable. All right. So now I have 1 over y plus 1 over L minus y. L is a number. dy. And I already took care of that side. All right. Now let's go over here, Lindsay. Ready? So what is the antiderivative of 1 over y? We know. What'd you say? LN. Yep, so that's going to be ln. Technically the absolute value of y, but y stands for population of something, right? That's growing, so we don't need the absolute value. Okay? Over here, be very careful. Remember, L's a number. Pretend it is 1 over 4 minus x. Like when you're using these odd variables that you're not used to, put them into friendly notation. And what would I need?
Negative.
There we go, Kaden, exactly. There's a negative because of that. It's technically USA, but we've done it so many times, right? So the natural, don't need the absolute value because the carrying capacity is the highest it could ever be, so that can't go negative. You guys are really intent. Are we following the proof? If you understand the models and where they come from, your brain won't have to work so hard trying to remember it 6 months from now. All right. How do we get rid of 1 over L? I would like to exponentiate, but I can't until I have a naked natural log. Yes, times L. So let's go do that. Ln y. This is all really good math somebody had to do before it went into a computer program. Right? If you were working with logistics growth right now, you would again just plug in data points. All right, so over here, I'd multiply by L and I'd get L, K, T plus C. Technically times L, but that's another constant, right? For it all makes sense. Now I still can't quite exponentiate because I don't have just a plain old natural log. So you need a little pre-calc or algebra 2 right here. When we subtract, how do we condense?
Right.
Excellent, yeah. So a lot of great math in this proof. All right, there we go. And this will equal. All right, it's fun. It's a lot of work. Don't show this to Calc 1. This is one of those days I say don't show Calc 1. They'll freak them out. But every step makes sense. It's just when they're all together, that's a daunting looking board right there. Now again, back to pre-calc. How do I undo this? Exponentiate. Yeah, so if you don't mind, I'm just going to go like this. E to the ln, that'd just be y over ln y. Now over here, okay, how did we deal with that when we used to do our x? I would technically have e to the lkt plus c, but can you anticipate what I'm going to do? Yes, it's technically from exponential algebra times e to the c when we multiply the outer exponents, and this is just another what? Constant. So C e to the L K T. I'm starting to morph into it. I have the solution down below. Do you kind of? It's getting there. It's just not quite there yet. My goal is to solve for y. If this was a heart, I could break it apart, but it's not. Are you allowed to flip things? Sure. Right? Let's go make it. Let's go do that. So at least I can get y. You only want y in there once, and so I've got a problem. Now, technically, if I flip this, I get 1 over it, correct? But isn't that the same as having a negative exponent? Isn't that 1 over it? Are you seeing the bottom morph? Do you see on the bottom there's, in the formula, there's a c e to the negative lkt? All right, now I need to solve this for y. There's a couple ways. But I think I'm just going to go like this, because I just want y in there once, and it's in there twice. So I'm just going to, it's a hard, I'll break it apart. There's several ways to approach it, but I like to be consistent with you guys, and we've always done that. Again, don't lose track. What am I trying to solve for? Y. I'm trying to get a model for figuring out what the population is at any given time when I know that its rate of change is following the logistics growth model. So let's go add that 1. Boy, that's really close, right? Can you see? You just did it. If you didn't see Lainey, she went like this. Just tell me multiply by y, right? And then divide. So can I do that in one step? Let's do it. All right, so I'll have L over 1 plus CE to the negative LK. I'm going to put that in parentheses like it is and a T there. Okay, what does that equal? Y. Now, if you were to Google logistics growth, there might be some changes. Again, what did I say? Some books or professors or texts might call that carrying capacity. Do you remember? A for amount, M for max is pretty common. That's probably the second most common. C isn't as common because if you call that C, then your constant has to be something else. So that gets a little messy. This is in parentheses because what do you get when you multiply two constants? Another constant, so there are some people who will make that its own lumped constant and maybe call it CE to the negative MT. Or even put the constant of a -1 in it. You know what I mean? So you can see how it can morph. I like this one because don't worry about this. The year I did that, they forgot it. So don't even, just cross that off. We're just going to find it every time. So here's your mnemonic for it. Let's go back. On my next page, in yours, do you guys have a cow in your notes or no? Do you have a picture of one? Nope. So this is how you're, I had a picture of it. Think of lice minus lift. I used to have a little picture up there of a cow licking its nose. Just there was lice on it. And it helps, because watch. It's an L on the top. 1 plus CE. What does that spell? Kind of lice. And then minus lift. So that does help you remember it. Here's the bonus. Generally, because do you think most kids across the world can remember that? No. So you usually don't have to work with the model directly. You have to recognize it. So what they might do, Lindsay, is it might say 500 over 1 plus C e to the -4t. Maybe this is even a 6. Represents the amount of bacteria present at any given time in this culture. What's the carrying capacity for the bacteria? 500, because you understand the model. See what I mean? So a lot of times it's just understanding the model, which is why we're putting so much time into it. So again, it says the most important point on our logistics X is that right there. It's the inflection point, correct? It's the point, so let's write that down. T, Y of T. Remember, Y is whatever's growing, so you have to be able to call that anything. C for COVID, R for radioactive material, whatever it is. Where the growth rate is the fastest. So I want you to go right here. dy dt, that would be the rate of growth, is at a max. Right when we hit this. Now take a look. Suppose this was up here at, let's say, how many people are in this school? I don't know. What's their school? Let's say 1,800. Does that sound about right?
4,500 grades, yeah.
Yeah, let's say 1,800. If you had to guess, this is one of those questions where I say, if I had a gun to your head, you don't know for sure, but if I did, right? And if this was 0, and if that was 1,800, and I said, guess right now, if you're right, I'll give you $1 million. What would you guess this is? Because it looks like it, in common sense, it kind of makes sense. What would you guess, Lainey?
900.
I would. And you are 100% correct. You are 100% correct. But you're saying because it looks halfway, correct?
Yeah.
Also, if you think about it, like the rumor scenario, once half the school knows it, won't the growth rate slow down? Because you're more likely to tell somebody who's already heard it. Does that make sense? So this is always at L over 2, but not because Priestley just said, well, it looks like it is. There's a mathematical reason. All right? So the mathematical reason is because the concavity changes, right? So it says, what does it seem like the population is when the growth rate is at its fastest? It looks like the population would be half of the carrying capacity. It is. But let's do the math for it. We can't just trust Priestley. He just guessed, right? It's a good guess. It looked great. But why wasn't it 904? Right? Okay, so let's go prove it. It says the maximum growth rate occurs when we reach half the carrying capacity. This starts with the fact that the inflection point is where our second derivative equals 0. So let's go see what makes our second derivative equal to 0. So let's write down our first one. You should now know the model for the rate of change. That's the Kiley model. When we solve for y, we get the L over 1 plus C e to the, all right? So it's kind of like our exponential growth. So you should write ky times L minus y. I'm going to take a second derivative, and I don't really want to use the product rule. So I'm going to distribute it. You okay with that? Just because I know it's easier, because I've done this 1,000 times. You could use the product rule and get the same. So I'm actually just going to go KLY minus KY squared. All right. Now I'm going to take my second derivative with respect to t. So I'm going to do this of both sides. And then you can even see why, we've talked about that, that's why they call it d squared y dt squared for the second derivative, right? So let's write that down, d squared y dt squared equals. Now be careful, in this first one, which is the variable, the k, the l, or the y? The y. This is all a constant right here. What's the derivative of any constant times the variable? If I said, what's the derivative of 5x dx? What would you say? Derivative of 5x dx. 5. What's the derivative of 5x dt? 5 dx dx. See, it's all there. It's just very in a situation you've never seen it before. So wouldn't that be just the constant times the derivative of the guts? How are we doing? A lot of theory today. I could skip today, and you'd still be successful, but I like you to understand why you're doing what you're doing. I have OCD. All right, this one I'll bring the power out front. I'll knock it down 1, right? Times what? dy dt. Now, at that inflection point where the growth rate is the fastest or where that logistic S starts to curve, right? What's our second derivative got to be? 0. So remember when we used to do it with that falling ladder and we go 2x dx dt plus 2y dy dt and we just cross those, the 2's off because they were in both of it? We can just divide everything. 0 divided by that is gone. So I actually have this, KL. How are we doing so far? I just divided, Aaron, you're nodding, right? I just divided everything through. What can I factor out of this? All right. This is really good theory here. All right. I need that. Now we're back to algebra 1. 0 product property. For a product to equal 0, either k has to equal 0, which it can't. It's a constant of proportionality, and if it was 0, we would have 0 growth. It would be, right? So L minus there, Priestley just thought, this has to be 0. And remember, we're trying to figure out what the size of the population is when it is growing the fastest. It's growing the fastest when its second derivative is 0. That would mean L has to equal 2y. So his guess was correct, right? So what is the population, no matter what, when the population is growing its fastest? The carrying capacity, right? Not just because I told you or because Priestley guessed, because it is. So watch the type of question you might get. That seems really complicated, and at the beginning of the hour you'd be going, what? Suppose that there's some population that was logistic, and we solved it, and we got 100 over 1 plus 2e to the negative 4t. And maybe in the stem of the problem it says what could be, let's say bacteria. Bacteria is growing logistically so that its solution curve follows this model. What is the size of the population when the population is growing the fastest? You should just go 50. Because you see what I mean? You understand the models, you'll be going, well, this is the carrying capacity right here. And it's growing the fastest at half of its carrying capacity. Make sense? All right, that's a lot of theory. We're going to keep going with theory. You don't have a whole lot. We're going to sum it all up, okay? Normally I put this on a note card, but I don't have them right now. So we're going to go over here, and we're going to do a little practice and just get everything we know about this curve on here. So go ahead and let's start right here, and let's sketch this. Okay, so we've got something changing over time. I am going to call it y. So over here is y of t. Let's put what we know about it. All right, it's going to help you sort stuff out. All right, first of all, let's draw that horizontal asymptote up here. It's what's limiting the growth. It'll never get past that. What variable am I going to put up here? F, thank you. Okay. Then I want you to write it as a limit. The limit as t goes to infinity, right? all of y of t actually equals L. You might say, why are you writing it like that? Here's a past AP question. Look at what it says. Did it say to, look at two. It's M for moose in a national park, not Y. See what I mean? This is still KY times L minus Y, sort of. Okay. But do you see what this says? It didn't say find the carrying capacity. Right? Amy's got to know. They're asking you for the carrying capacity. So let's go put that up there. Go right here. Okay, this is a point. It's t comma y of t, but stuff happens at this point. We now know that its height is at L over 2. We just proved it, right? We went through a lot of time to prove it. Here's some other stuff we know. That this is where dy dt, the growth, is at a max. Remember, a function's at a max when its derivative, or the second derivative in this case, is 0. Make sense? Okay, so if they ask you for questions about when dy dt is at a max, you're going to go, oh, that's when it's growing the fastest. That's at that turn in the S. That's at half the carrying capacity. You see how your brain's going to work through the model? You guys are super understanding this. There's something else really important about up here. That's going to help you take a shortcut if you understand it. If not, you're going to have to do it the wrong way. What happens to the rate of change of growth as t goes to infinity? And don't flirt it. But what is dy dt doing as t goes to infinity? There. Okay? So if they mess with the model on you, it's not like in the right form, but you're like, I know they're asking me for the carrying capacity, right? And I know that the growth rate at the carrying capacity is going to approach 0. You can take some shortcuts. And here's an example of that. So let's go take a look at this guy. So here's a 2003 number 21. So it went to Pen Calculator Active. You would look at this, and you would say this is directly proportional to, and it just doesn't quite look right. So let's go up here. Off on the side, let's write dy dt equals ky times L minus y. Go ahead and write that. Sometimes you see it like that. Sometimes you see it, that's the main one. So go ahead and star that guy. Sometimes you'll see it as ky times, and then it is 1 minus y over L. You okay with that? But then, since this got divided by L, this kind of changes. But it's still a constant. Right? Sometimes you'll see this distributed and you'll be like, what? That doesn't look quite right. And if you don't want to have to morph them, so I'm going to go LKY minus KY squared. These are all differential equations that model logistics growth. They're just in 3 different forms, right? So if Caden's like, I don't want to work with the 3 different forms. What's consistent for all of these forms is that this approaches 0, right? As y approaches the carrying capacity. So watch how you can do these in your head. I went through all of that, 33 minutes, so that if you understand the models, this is going to be a really easy question. So let's pick, it's our first one though. So this first one might seem a little goofy. It says the number of moose in a national park is modeled by, and they did tell you it was logistics. So maybe Caden's bothered by the fact that this isn't KYL minus Y. And he's like, well, I better transform it into that model. He could, but he doesn't need to. He could write it like this, as 200 minus M all over 200. Does that make sense? And he could put the 0.6 right here. You guys are still with me, which is good. But since he divided by 200, he could go like this, and it just changes that. Now it's ky times L minus y. What's the carrying capacity? And if you're like, I didn't get that, that's the whole reason I went through. Because I said no matter what, that if we're looking for this, it means the carrying capacity. And what's the rate of change as we approach the carrying capacity? 0. So all you need to do is say, hey, this has to equal 0. Well, that can't. So 1 minus m over 200 has to equal 0. What is the carrying capacity? What would make that equal to 0? 200. Done. What's the population when the moose are growing the fastest? 100, Ellie. Yeah. See how it can be easy because you were paying attention so much you get the models? So let's go try another one. You try this one. See if you, and then actually we might just quit and go try a little delta math, but I might do 2 more. Go ahead and try this multiple choice question because logistics is almost always multiple choice, but just in case it's not, we're going to do an FRQ tomorrow. Today was just knowing the model. You can see I circled the answer there, but you should know why it is what it is, right? So I'm going to let you kind of absorb why it is what it is. This doesn't affect anything, by the way. What's that telling you? What does P of 0 equal 3,000 mean in this problem? Yeah, it's an initial population. I do have to add something up above because it just triggered something in my brain. But let's go take a look at this. So it says P of T is a logistic differential equation modeled by, here it is, this is the rate that it's changing. It's not quite in the right form. You can morph it into the right form if you want, but you better know that this is asking you for the carrying capacity, right? The slope of the tangent line or the derivative at the carrying capacity is 0. You need this to be 0, which either means the population is 0, which doesn't make sense because it's growing, correct? Or 2 minus P over 5,000 is 0. So really all Aaron has to do is I need P over 2,000 to equal 2. What's the answer? 10,000. What's the population when the species is growing the fastest? 5,000. You see the difference in the questions? Now here's another one. Okay, last up. You are in charge of stocking fish in a pond with, actually I listened to this one. It's coming back to me at some point. Suppose you're in charge of stocking fish in a pond at a rate so that the population growth is modeled by this DQ. Well, that doesn't look right at all. You know what happened? The KY got dumped in. In this case, it was the KP, right? But it doesn't matter, Kaden. You don't need to morph it that. You don't need to be like, I'm going to factor out a 0.02p and get it in the correct model. He just needs to know to set that equal to what? To find hidden in notation. So these can be really hard for kids because, wait, what's this? So Shunk, what is this asking you to find?
Capacity.
Yeah, the carrying capacity, the limit as t goes to infinity of p, right? So here's my p of t. It's asking you to find that. What is the growth rate as I approach the carrying capacity? You understand that you don't have to work with 3 different models, just one. It's got to be 0, correct? So Laney's going to say, well, I need 8p minus 0.02p to equal 0. Oops, sorry, p squared. That's algebra 1. Hidden in a hugely difficult BC calculus question, correct? This is really just solve a quadratic equation, right? Factor out a p. This can't be 0. Are we good? So 0.02p has to equal 8. You don't have a calculator, who cares? This is 2 100ths. Has to equal 8. You're nodding, right? It's there. As long as you understand the models, this is really easy. We're going to do this one tomorrow. So what's my answer for what Shunk said was the carrying capacity for the fish in that pond? 400. Now I have to have you go back up to the top because this does actually pop up and I neglected to. I wonder if I have room up on top. I have room, but Hannah might not be able to see it. It is possible to come in from above your carrying capacity, which is weird. And I remember saying that to kids one year, and I said, I can't think of a situation like that. And they used, actually, they had gone to SOC, and they used a science teacher at SOC. This was years ago, so I don't know if you ever had her. But they said she had a fish tank, and she'd always put too many fish in the tank, and so they were always floaters. They said it's I don't remember what they said the name was, but they said that they said it's like Mrs. Whatever's fish tank. It could only support so much, and she put in more than it could support from the beginning. That would be coming in above your carrying capacity. What's going to happen to stuff instantly? It's going to die off until it reaches it. Correct? So it is possible for you to come in from above, but watch about the math that happens with that. If you come in from above your carrying capacity, so suppose this was at 500 fish, and I dumped 800 in the tank. That you would have to know that if they said fish at times 0 is 800, your brain has, this happened once on an AP question, that's why I'm going back to it, and it's going to happen on your worksheet tomorrow. You have to go, uh-oh, I'm over the carrying capacity, correct? So, what is, let's call it fish. What is d fish, dt? Always. The fish is decreasing, so df dt is always negative, correct? So I might ask you, what's df dt if f of 0 equals 800? And Peyton's going to have to go, okay, I came in from above the carrying capacity, I'm dying off, it's decreasing, and so its rate of change is negative. Yeah, cool, right? Not only that, it might ask about concavity. So it might say, where is d squared fish and dt squared greater than 0? And if you're below the carrying capacity, wouldn't it be from 0 to 1/2 L? Right? Concave down from 1/2 L on out to what? Infinity. If you came in from above your carrying capacity, concave up where? From 0 on out to infinity. So you see, there's really complex questions, but if you understand the model and the Calc 1 behind it, you're good. I do want to give you an opportunity to try at least one of the delta math. They're short. They're whether you understand the model. I actually kind of so there's, I think, 6 or 5. So Hannah, if you're listening to this, there's some in delta math for you to do, but not much.